Good morning, good afternoon, good evening. Welcome to this session of the IAEA Nuclear Backend webinar series. Today's webinar covers accident-tolerant fuels and their impact on spent fuel management. With no further ado, I hand the floor to our host, Ms. Amparo González Espartero.
Hello, everybody. Thank you, Andrea. Good afternoon, morning, and evening. Welcome to this webinar, and let me introduce myself. My name is Amparo González Espartero. I'm team leader of spent fuel management in the nuclear fuel cycle and materials section in the IAEA since 2015. I'm very honored to moderate the webinar today with three distinguished panelists that I'm going to introduce by order of intervention. Mr. David Hambley is the Laboratory Fellow for Spent Fuel Management and Disposal at the National Nuclear Laboratory in UK. He is responsible for leading NNL's activities to support the interim storage of spent oxide fuels, the remediation and interim storage of legacy uranium metal fuels, and for evaluating the management of new fuel designs and fuels from advanced reactors. He is also actively involved in research into the behavior of the irradiated fuels in repository environments. He has more than 30 years of experience working in the nuclear power industry, including positions with the UK Atomic Energy Authority and other relevant organizations. He is involved in international activities on spent fuel storage at the IAEA, the World Nuclear Association, EPRI, and European projects Horizon 2020. Then Mr. Mikhail Beshunov. He joined the IAEA in 2016 as team leader of fuel engineering at the nuclear fuel cycle and materials section. Before that, he worked for 35 years in R&D in material science, studying physicochemical interactions of materials in severe accident conditions and behavior of irradiated fuel materials. Since 1989, he was head of laboratory at the Nuclear Safety Institute, IBRI, of the Russian Academy of Science, being responsible for fuel performance and safety modeling and participating as project manager in several national and international projects on fuel performance codes, development and applications for light water reactors and fast reactors. For several years, he was visiting as a scientist in the European research centers of Karlsruhe, ISPRA, and Petten, and he served as full professor in Moscow Institute of Physics and Technology since 1995. And Mr. Aladar Santos is a technical executive in the fuel, chemistry, low-level waste, and high-level waste group in the nuclear sector in the Electric Power Research Institute in the United States since 2016. Prior to joining EPRI, he spent 16 years at the American Nuclear Regulatory Commission in various capacities, serving as the chief of the renewables and materials and long-term spent fuel management branches, leading teams of engineers responsible for technical safety reviews of commercial transportation and spent fuel storage cask designs and consolidated interim spent fuel storage facilities. He also served as a senior materials engineer for the Yucca Mountain Repository Program, and he worked at the Center for Naval Analysis and conducted operational research studies for the U.S. Navy and Marine Corps. So after introducing the speakers, let me briefly introduce the webinar, which is focusing on evolutionary accident-tolerant fuel designs, which are those to be deployed in the near future, in a decade or so, and what will be the impact in the different steps of their management once they are discharged from the reactor core, as storage, transportation, recycling, and their final disposal. The three presentations today are complementary and will provide an overview of the different evolutionary accident-tolerant fuel designs, the potential implications of these designs may have on the back-end activities, highlighting the importance of addressing the nuclear fuel cycle in an integrated manner, and current and future international collaborative R&D efforts in this field worldwide. So the webinar will last 90 minutes with the 3 presentations in a row and with an allocated time of 20-25 minutes at the end for questions and general discussions. So please type your questions in the Q&A chat to have them available for the discussion after the presentations. So we have prepared the webinar very carefully, and we hope you will find it interesting, useful, and informative. So without more delays, I will leave the floor to Mr. Hambley, that will talk about an assessment of the management of advanced fuels after discharge from the reactor core. So, David, the floor is yours.
Thank you very much, Amparo. And my presentation today is to provide an overview of accident-tolerant fuels, their development, and the trends in terms of their future behaviors. And thank you very much. So this is based on some work that was done for the Spent Fuel Storage Conference some years ago, and it's been updated several times since to reflect the evolving position with ATF. Briefly, I'm going to introduce what accident-tolerant fuels, where they came from, and what the potential impacts are, and then briefly give a summary of the main aspects associated with the most common types of cladding and fuel that are currently being considered, and then give a brief summary of where that leaves in the position. And subsequent presentations will go into more detail on particular aspects of this. So accident-tolerant fuels arose as a response to the Fukushima accident in 2011. In particular, the idea was to seek to improve the accident tolerance, the length of time fuel could survive under severe accident conditions, to allow improved capacity for management of severe accidents. It must be said that a lot of work done on analyzing the accident at Fukushima Daiichi, however, very little has so far focused on the spent fuel management aspects, and it's now very timely that these are under consideration. In terms of the concepts of what might an accident-tolerant fuel look like, there are two strands. One relates to cladding, and one relates to fuel. The cladding is primarily there to protect the fuel, and the improvements are to seek a cladding that will last longer in the extreme conditions. So we have coated zirconium alloys. People are also looking at aluminium alloys and silicon carbide composites are the three main types of modifications for the cladding being considered. Of those, the chromium-coated zirconium alloys are those that are most close to deployment or in the process of evaluation. The fuel aspect really is developments are proposed there to improve the economics and to make accident-tolerant fuels more attractive for reactor operators. And there we're looking at doped UO2, advanced UO2, which allows us to go to higher burnups and higher enrichments, thereby also reducing the amount of fuel we need. And finally, continued investigation in higher density fuels, which allows better irradiation performance. Briefly, in terms of the impact of ATF, what do we mean? For us, spent fuel management means what happens to the fuel and how we manage it from its discharge from the reactor through storage, transport, and until it's disposed of in a repository. We also consider management of the fuel up to reprocessing if that's a chosen route. This is just to highlight that it's not just accident tolerance. We must have a product that is usable and deployable into nuclear reactors in a cost-effective way. And a lot of work has been done more recently looking at the economics of how we deploy the near-term options. I put a little brief slide here, and Al Santos will go into this in much more detail in his later presentation. So moving on to have a closer look at the claddings now. The first cladding and the most advanced options are associated with coating the zirconium alloy with a non-reactive coating, of which chromium has been the most attractive option and the one which is furthest towards deployment. In these, chromium is deposited as a very thin layer on top of the zirconium cladding. It provides a non-reactive surface which produces a chrome dioxide surface layer, which continues to protect the cladding up to much higher temperatures and delays the onset of any zirconium steam reaction. The pictures you see here are of the chromium coated cladding in the bottom left-hand corner. In the top right-hand corner is a cross section, and the very bright layer at the top shows the thickness of the chromium coating, which is very thin but very well adhered. And the bottom left shows a more detailed example of the coating. And you can see immediately the effectiveness of the coating through, this is a defect in the cladding coating that was deliberately left there to explore and demonstrate the effects of oxidation. So in terms of thinking about their impact on the back end, chromium coating significantly reduces weight gain during steam testing. So hydrogen production is also reduced in normal operations, and therefore the risk of hydride formation during subsequent storage or reorientation during subsequent storage is also much reduced. And in general, we expect that the performance will not be adversely affected, whether that's in storage, transport, reprocessing, or disposal. The failure site characteristics and matrix corrosion are not expected to be adversely affected. And there's a question about maybe putting a large amount of chromium into a repository system might give rise to some chromate levels in the repository, which might alter water chemistry. And that's something that would need to be looked at in the future. But overall, these are not expected to have a significant impact on the back end. Moving on to iron alloys. The iron alloys have been used in the past and are still used in some reactor systems. In general, they have a neutron penalty, and zirconium in water reactor systems offers better corrosion performance. However, the alloys under consideration include aluminium for higher temperature oxidation and an iron-chrome mix that provides a protective layer under normal operating conditions. In terms of the impact on the back end of this presence of steel clad, we know from experience that stainless steels corrode very slowly over very long periods of time. In some cases, or some combinations of temperature and neutron irradiation, depletion of chromium at grain boundaries can occur, and that can lead to sensitization. Although the extent depends on exactly the grade of steel and the irradiation conditions, and storage conditions that mitigate the risk associated with corrosion have been established around the world. And therefore, so long as the sensitization of the stainless steel is compensated for, the presence of steel as a cladding is not expected to generate any significant issues during back-end management. Looking briefly now at silicon carbide composites, these are very different from current cladding materials. very attractive due to their high temperature oxidation resistance and low neutron absorption. However, they are novel. There are challenges around the cost of manufacturing, the ability to manufacture the fuels, and their long-term hydrothermal behavior. This is seen as a much longer-term development opportunity, and research is ongoing on that, and it's important that as that research progresses, that consideration of the conditions in the back end of the fuel cycle are also taken on board, and that can be done effectively during the development programs. There's very little data on the behavior of silicon carbide composites post-irradiation. There are one and two anecdotal evidence from the management of research and development fuels, but there isn't need for a systematic evaluation of their behavior after irradiation under relevant conditions. Finally, I'm going to talk briefly about potential changes in the fuel itself. In terms of improving the fuel, to reduce the temperature inside the fuel during accident conditions, it's possible to dope the fuels to improve their thermal conductivity and or to change the grain size so that fission gas release is reduced. Work was already well underway looking at chromium doping for larger grains to reduce fission gas release, and further work on that is expected to continue. I should just say that on the doped fuels, they're not expected to have a significant impact on the back end, although the effect of additives on oxidation behavior would need to be confirmed, but it's more expected to be a confirmation than a source of concern. Looking at the other higher density fuels, a large number have been examined over the years, and some are still under consideration for fast reactor applications. They are, however, in general, much more reactive than uranium dioxide. The four listed here have all been looked at to some extent during the recent years, and in both the carbides and the silicides have fallen by the wayside as a result of their poor reactivity with water. The main contenders still under development at the moment are nitride fuels, where continued work on doping and modifying the fuel to enhance its resistivity to water exposure are still underway. These are much longer term prospects, as there are challenges both in the fuel development, manufacturing, and also in demonstrating compatibility with irradiation conditions. If we think about the back end, reactivity with water and air remain issues for storage, transport, and disposal. And although the temperatures are much lower under these conditions, the duration of exposure is also potentially much longer, and therefore behavior of irradiated materials under less extreme conditions needs to be understood. The mechanisms may also be slightly different, although that mainly relates to silicides rather than oxide and nitride forms. In reactor performance, improvements in terms of stability of exposure to water will automatically help the management of these materials in the back end. Reprocessing of the higher density fuels should be feasible, and likewise recycling, but they are more challenging than current standard oxide fuel reprocessing. The near-term deployment option would be to increase the enrichment of existing UO2 fuels. And there, the challenges are less, but there are still some challenges, particularly around criticality of having sufficient data to back up the validation of safety and inventory codes. The potential higher individual assembly heat loads would need consideration and might result in changes to the design of storage systems, although it's not expected to affect the fundamental basis of storage systems that we currently have. And there's a potential for higher operational doses from higher burn-up fuels. Again, these can be managed by design adaptations to existing systems. And the MOX experience indicates that higher enrichments and their effects can be adequately managed if you're looking at reprocessing. There are lots of activities underway looking at the behavior of fuel and cladding in storage, transport, and disposal. Some of them are listed here, and these are valuable contributions to making sure that we can manage the back end, and that the new fuels do not present unexpected problems for their future management. So in summary, imagine the spent fuel is being given from accident tolerant or advanced fuels is being given the level of consideration. And it's important that it's done at this stage before fuels reach final deployment so that we don't end up with any unexpected negative effects on the management once they're discharged. Those nearest deployment are expected to have a minimal impact on our ability to store and dispose them within the sorts of technologies we have at the moment. For higher density fuels, there remain to be challenges before they're shown to be acceptable. And both them and silicon carbide claddings would require substantial further work before we could be sure that they're manageable in the back end. But such testing and validation could effectively be incorporated into the development programs in a cost-effective way. Thank you. That concludes my presentation.
Thank you very much, David. This very comprehensive overview of the different accident-tolerant fuel designs in terms of changes in the cladding and the fuel itself, and the main aspects that might impact the backend. So this is the overview, and now let's move to the next speaker, that is Mr. Beshunov, and he will present an overview of the recent and current IAEA coordinated research projects on accident-tolerant fuels. So, Mikhail, the floor is yours.
Yeah. Thank you very much, Amparo, for your introduction. Hello to everybody. After this excellent overview of ATF materials and approaches, in my presentation, I will focus on research in this area, which, as you know, is carried out in many countries currently. And one of the important mandates of our agency is to coordinate national research projects. And so we do it within the so-called coordinated research projects, where participants from many member states participate, representing the national projects. So on ATF, we recently finished the first coordinated research project, or CRP, ACTOF, and recently we started a new one, ATF-TS, and abbreviations I will talk later. So, yeah, I will start in more details about talking about ACTOF, analysis of options and experimental examination of fuels with increased accident tolerance, which took place from 2014 during four years till 19, with the main objectives to support options for development of ATF fuels, to support modeling of new fuel designs, and to acquire data through experiments. In this, CRP was relatively large. We had 17 organizations our participants are organizations represented by chief investigators from 13 member states. Here you can see the list: Argentina, Brazil, China, three institutes: Finland, Germany, India, Italy, Korea, Poland, Russia, 2 institutes, United States, 2 institutes, Czech Republic, and Japan. And traditionally we have observers, and in this CRP we had our constant observer, permanent observer from OECD NAA, EPRI, US NRC, and GRS from Germany, who was active participants and participated in our benchmarks. So, as I explained recently, the project was finished, and we have already published the tech doc with the main results, which is you can find on IAEA site, open access. And you see, normally CRP includes individual tasks, but most important part of the project is joint actions, where several activities, collaborative, are carried out. In this case, we had round-robin tests, benchmark exercise, and joint exercise of experimental modeling for severe accident conditions. Yes, and I will briefly talk you about main results at first of this experimental project, work package round-robin tests, where we had 7 participants listed here, coordinated by Westinghouse Electric Company, also Czech Technical University, who collaborated with UGP Prague Research Institute and Hungarian Academy of Science Institute, also KIT from Germany, VTT from Finland, Institute of Nuclear Chemistry and Technology from Poland, and University of São Paulo from Brazil. And in this table, you can see how this exercise was arranged. There were 3 tasks: sample production, long-term corrosion test, and high-temperature oxidation tests. And each participant participated in one or several these tasks. And for instance, you can see University of São Paulo provided their samples, but did not participate in experiments. And for instance, Hungarians only run experiments, but several participants participated in the whole, in all 3 exercises stages. So, briefly talking about first part, preparation of samples. Eventually, we had the participants prepared 4 types of ATF candidate cladding samples, which were mainly coated cladding concepts and advanced steel. So as you can see here, CTU, Czech University, with his collaborators, provided chromium-coated zircaloy 2 samples and zirconium 1% niobium E110 alloy claddings. As you can see lower, these samples, which were coated by participants, were provided by Westinghouse for zircaloy 2 substrates for these coatings, and UGP Prague provided alloy 110 as substrates from this alloy. And then participants prepared these coatings, chromium, this more complicated so-called max phase coating. Then Polish Institute prepared their own design, and University from Brazil used their advanced stainless steel. Yeah, and few slides about main results, more interesting. So you remember there were different series of tests. First of all was autoclave long-term corrosion test. And here you can see the table to the right and the graph representing this data. It was weight gains measured from corrosion test on different samples. And here you can see blue line is reference zircaloy 2 material. And then you red zircaloy 4 and green lines are chromium coated samples. And here you can compare weight change in different experiments. Here in more details, you can see the figures. And sometimes, as it was with max phase coatings, you can see that very strong spallation effect was observed. So eventually there was no gain, but loss of material. For this reason, you cannot see it in the left graph. Relatively good behavior for the steel samples, but the best, of course, you can see chromium coated samples. Another type of the test with this type of samples was high temperature oxidation, typical for accidental conditions. And here again, different samples were compared. And on the left-hand side graph, you can see a theoretical curve, so-called Cathcart-Pavel correlation for high temperature oxidation, and results of testing. So naturally red, it's basic without samples without reference samples without coating, which belongs to this line, but mainly all test samples showed much better behavior. However, again, in some cases, it was not the real, as it seems from this picture, because in this type of test, high temperature oxidation, samples of steel from Brazil, as you remember, despite its this is green data, despite weight gain was small, but these small values were related mainly to strong spallation effect. You can see on these photographs. And for this reason, the main criterion eventually was chosen hydrogen produced. And then you can see that if a black line is reference zirconium alloy claddings, so due to this spallation effect, oxidation of steel was very high, and then other were better than standard zircaloy, and again you can see the best behavior is chromium coated samples, and this is also shown on this picture. You see this is two samples without zirconium 2 without coating and with chromium coating, 1200 centigrade for 30 minutes both, and here you can see oxide layer thickness and chromium on the lower, which is much lower. And a special attention was paid to test on residual ductility, and this was, we only started this exercise, but it will be certainly continued in the new CRP, in the next one, since because of this effect of very small oxide layers, the traditional ECR criterion 17% is cannot be used because oxides are very small, and this is the main contribution to oxidation to ECR. But on the other hand, ductility of these samples also increases, sometimes significantly. And here, many countries now work on new criterions. And also some preliminary results are shown on this picture, but I will not talk in details. So now talking about another exercise, as you remember, we had organized benchmark. In this case, it was comparison behavior of Tecral against standard zircaloy 4. This exercise was organized by INL, Idaho National Laboratory, who provide modeling input, normal operation case specification for 2 cases, U2 with Fekral and with Zerkaloi 4, and LOCA case specification. It was 2 different exercises, and also output format in order to, and after this, to analyze, to compare, and all the results. And very briefly, yeah, we had in this exercise, we had 6 participants: INL with Bison code, Nina from Italy with a Transuranus code, University of Sao Paulo with modified FRAPCON code, Argentina with their national BACO code, and Japan with JAA with FEMAXI. And okay, here you can see some examples of calculations. On the left side, Hoop stresses in the exercise on normal operation conditions, blue for Zerkaloi, red for Fekral, and to the right hand side, burst pressure also for different red or different codes, different materials, and against experimental gray bars. Okay, without no time to go into details, just short formulation that benchmark was organized and finalized where the extended codes were compared for the analysis of fuel rod with Fekral cladding under both normal operation and design accident conditions. And the third work package, as I mentioned before, was severe accident experimental modeling exercise, which was prepared by KIT, who shortly before this, our CRP carried out a new test, Quench 19, with Fekral cladding. It was an international test. Materials were provided by United States, Argonne Laboratory, and they used these materials, cladding materials, in the bundle facility of KIT, Quench 19 with Fekral claddings. And this data were analyzed using 2 severe accident codes, 2 participants at that time. We had JRS from Germany with Atlet CD, and Ibraya from Russia participated with the Russian code Sakrat. Sorry. Yeah, again, just a couple of examples. For instance, left picture shows relatively good representation of temperatures, measured temperatures in calculations. And however, the most important result, hydrogen production, was strongly underestimated. And this was the reason why we took the decision to continue this exercise in the new CRP. But in this case, we'll have more codes, not only these 2, but also such codes as Melkor, Aztec, and so on. So now I have several minutes to talk about the new project, new CRP, testing and simulation of advanced technology fuels, ATFTS, which was launched recently, also foreseen for 4 years. As usually, it was advised we have such technical working group on fuel performance and technology, which normally make recommendations to our section what type of activities to plan in our programmatic plans. Before starting this CRP, we organized technical meeting where this CRP was on fuel behavior in accident conditions, where we had a special technical session on this topic, and the proposals were collected. Then next preliminary step was a consultancy meeting on preparation of new CRP proposal. And then it was submitted to IAEA committee, which approved it. And so currently we are waiting we wanted to organize the first RCM this summer, but due to COVID, we decided to shift it to March and hope we will be able to organize it face-to-face. So currently we have 18 participants, agreements and contracts, but the project is still open for new participants. And research objectives similar to the previous one, but in more detail, since the first CRP we can consider as preparatory for the second one. And here we have also experimental program, I mean joint activities, separately from individual efforts. So here we are planning to have round-robin tests on coated cladding. So this, you remember that in the first CRP it was mainly oxidation, high temperature, and autoclave corrosion test. For this reason, here we'll focus more on thermomechanical behavior. For instance, ballooning, burst isothermal test, ballooning and burst transient, locker test, using different, this is preliminary facilities, because finally all activities will be coordinated and approved at the first RCM. Also, we are going to perform joint tests with FECRAL, starting with high temperature oxidation tests, autoclave oxidation tests, and probably thermomechanical behavior as well. Silicon carbide, we are not sure, but still planning. Then very interesting, we have very interesting proposal from CREEP Japan. They have a new test facility for severe accident testing, and they propose to perform tests with coated zircaloy 4 under severe oxidation conditions or LOCA. It will be also decided at the first RCM. And also traditionally, Halden project share the reactor test data with our CRPs, and we have preliminary agreement that they will share the data with doped fuel pellets, which were tested in Halden reactor for our benchmark. And so correspondingly, in this slide, you can see our plans for modeling program. So since I should finish soon, I will just mention in modeling program, we have fuel performance codes benchmarks, including modeling improvements and uncertainty analysis. Here you can read later maybe some details, including this Halden test. Then we have severe accident modeling benchmarks. As I already mentioned, we hope to have a degree facility test data. But while waiting for new experimental data, we shall start with Quench 19 test, continue, as I mentioned before. And in this exercise, we'll have more mod codes. As I told you, Aztec, Atlet CD, Melkor, maybe Socrat as well are expected to participate. And also the third work package will be organized by Tractable, local evaluation methodology development for nuclear power plant applications, more practical approach, how to exercise, how to use fuel performance code for licensing, because Tractable is involved in licensing, and so they prepare such exercise, including uncertainty analysis in application for new materials, in this case, ATF materials. So I think that's all. Thank you very much for your attention, and welcome to the new CRP, where you have still an opportunity to join us, if not yet. Thank you very much.
Thank you very much, Mikhail, for this very interesting overview of the international R&D efforts on the design of ATFs and the associated post-irradiation examination tests coordinated by the IAEA. So let's move to the third speaker, that is on the efforts of EPRI, gathering different actors participating in USA R&D on ATFs, and it will be delivered by Mr. Santos. So Al, the floor is yours.
Thank you, Amparo. Can you hear me?
You can.
Okay. All right. I'll go ahead and go over my presentation. So I wanted to give a background, give an update on what we're doing here in the United States, looking into the use of ATF, accident-tolerant fuels, or advanced technology fuels, whichever you want to use. But this started off in 2012, where our Congress mandated to the Department of Energy to develop light water reactor fuels with enhanced accident tolerance, and wanted to have loadings by 2022. There was a three-phase process, or a three-phase strategy. We're now into this, basically the second and third phases in between the two, and the utilities are committed, and you'll see here in the near future here that or the next slide that we were able to load in the U.S. Fuel in 2018 LTAs of two different types of accident-tolerant fuels. So we beat this by 4 years. And if you want to take a read through some of the report that was submitted to Congress, this June 2015 report is available online. The one thing we want to talk about is that, as you heard about, we were talking from Amparo and David and others, that we're looking at the near-term ATF concepts. And that's because those incremental benefits are really easier to get and more and can be accelerated or deployed in a faster time period. And that's a critical factor, because traditionally in the U.S. there's a long time frame from design to deployment of new fuel concepts. We don't have the time to spend on another 15 to 20 year project to develop new fuels to be then implemented. And the reason for that is that there are, we're losing more and more facilities like Halden, and so we need to do this testing and get the data to support the licensing now while there are facilities. And then you're looking at that we have an abundant supply of R&D programs. So you can see the activities that are going on here at IAEA, at OECD NEA, and also with ourselves at EPRI and the Department of Energy, et cetera. And so, but this is the key attribute that what I would like to talk about, and what's going to be driving a lot of the discussion today in our slides, which is from EPRI. If you take a look at this graphic, and it's not, it's probably about a year or so old, but it gives the same information, which is that we really can't wait. We're here at 2020, and you can see this is what was projected in terms of the fleet in the United States back in about 2 years ago. And we're looking at here at 80-year life of plants and 60-year life of plants, and then this is the actual. These are the number of plants that have decided to shut down due to economic reasons and other reasons. And so you can see that we don't really have the time to waste to try to get new fuel implemented, because the diminishing returns on new fuel when you have less reactors to utilize them. So the U.S. industry is a milestone, and it's what they're shooting for is deployment in the mid-2020s for battery loads of ATF. And that is including both dope pellets, as David was talking about earlier with dope pellets, and coated cladding. Now, farther down the road, we're talking about also increased enrichments to realize higher burnups. And we have to realize that is a heavy lift, both for the industry and the regulator. So I'll talk about now about some of the activities that we're looking at here at EPRI. What we did back in 2016 to 2019 was develop scoping studies looking at the safety benefits associated with the different ATF concepts, both the near-term and the longer-term concepts, and converted them into economic benefits And you can see here that that was to develop the industry ATF business case. I'll show you some of the reports that we have, but there are some reports that are proprietary and some of them that are available to the public. You can get a glean on the business case. We have developed the business case report and such, but that's proprietary to our members, utility members. But you can get a glean of what those cost benefits are from our public report, and you'll see them in my summary slide. But basically, what we have here is we have the cost of the R&D, cost of the licensing, and also the cost for utility implementation. All right, those are all significant costs. And then on this side, you have that with the fuel utilization and fuel, and these are in order of the benefits in terms of the impact in terms of savings, is that fuel utilization for higher burnup, fuel efficiency with higher enrichment, operational flexibility, meaning that if you have improved safety, you can then have more operational flexibility because you now have more margins. And then, of course, increased fuel reliability. So in summary, and as a high-level summary, and of course, you can go to the reports to download and get much more details. We looked into severe accident analysis. We looked into design basis accidents, anticipated operational occurrences, as well as normal conditions. And so what you have here is that the safety benefits vary among the ATF cladding fuel concepts. We looked at a variety of different ones and probably hundreds of different cases. And we looked in these scenarios, and it really the benefits, the safety benefits, really depend on your cladding types, your fuel concepts, your design accident scenarios, your beyond design-based accident scenarios, in your AOOs, and then your reactor types. PWR and PWR act differently, and also different types of PWRs act differently. We did see coping times as low as just a few minutes to as high as 3 hours for some of these concepts, okay, for severe accidents. But this is important to note here that ATF, while it can delay core damage, you still need the restoration of the core cooling to prevent the core damage. And that's a really important concept to understand, that we are not creating a meltdown-proof fuel. It is a delayed fuel, okay, for core damage. And so when we look at specific examples, we did look at a Fukushima case, and we did look at 3 Mile Island. And this upper picture here, this other graph here, is an indication of the TMI2 core molten core mass as a function of time during the accident, and the different concepts that we had up here for the ATF fuel concepts. And you can see here that this is the ZERC UO2 system, and the coated claddings, the silicon carbide, and the FECRL, or ironclad, as it's called, they all have a much lower molten core mass compared to what occurred during the 3 Mile Island event. Okay, so you can see here that ATF would have limited the accident core damage at 3 Mile Island. For design-based accidents, in this AOO in particular, this is a PWR loss of feed water and feed and bleed case, where we have 300 GPM of water being injected 3 hours after the accident scenario. And in this case, what you see here is that the three ATF concepts, the ZERC, coated ZERC, the FECRL, and silicon carbide, all turn the decay heat curves over so that you could prevent a core damage event here. And so you can see here that these concepts do have an accident tolerance feature that can provide increased margins, and that's a big part to how then what we can do is looking into the operational enhancements that come about from those safety margin improvements. And lastly, I just want to say that we got an agreement from most of the participants that were in this, the general agreement and consensus from the participants. This is a graphic showing, David showed the different concepts. I wanted to show some of the potential benefits of the coated claddings, because this is where the U.S. utilities are going today. And in this case, what you have here is that this is a key aspect here, which is that NRC has done a really good job, in our regulator in the United States, looking into the regulatory requirements or the regulatory framework, and this doesn't mean that there are data needs. There are substantial data needs associated with this, but both the ATF, there's a document out there, NRC ISG 01, and it was drafted back in January of 2020. You can download those from NRC's website, and that goes into a lot of the details over the framework for the whole fuel cycle, from the front end all the way to the back end. And in this case, there's also a presentation that just came out 2 weeks ago from the EPRI Extended Storage and Collaboration Program meeting, the virtual meeting that we held, where NRC presented a very good summary of the issues and for the front end and also for the back end, and that was very informative and very useful for us. The enhanced scoping times I talked about earlier, reduced potential for fuel relocation. Here is local accidents local accident experiments that were provided by Westinghouse Corporation, looking into the chromium coated versus the Zerlo. And you can see here that the opening size of these events, the burst opening sizes, are much smaller than the Zerlo, which then reduces the amount of fuel relocation during locus. And so, and that then enables us possibly to go to higher enrichments to realize higher burnup. And that's a key aspect of this work. And the experiments that are, so all that is being done, and this is, I guess, so David was talking about earlier, which is that I want to go into a little bit more detail about this graphic, which is showing why in the U.S. The utilities are moving for coated claddings with higher enrichment and higher burnup. So you have these enhanced safety pieces here: enhanced fuel performance, enhanced fuel reliability, improved operational flexibilities from the increased margins, safety margins, and then you have here this fuel cycle optimization. We have several reports looking into that, optimizing the fuel cycle with higher enrichments and higher burnups. That will lead, that provides the economic benefits that enables the ATF and the enhanced safety of the ATF to be adopted more rapidly in the United States, making the market is driving the improved safety in this case. And what is the market? The market is 20% less waste, so more efficient use of the fuel. So that reduces the cost burdens for waste disposal, waste storage, which is a savings of about $3.5 billion for our U.S. fleet. Then on top of that, you have, with the increase in enrichment and higher burnups, about almost a $9.5 billion in savings for the fuel savings. That enables a 24-month cycle, which then creates, that's the driver that then implements the enhanced safety with the adoption of ATF. And so to show that it's real, these are the utilities and the sites that are emplacing different types of these ATF concepts, fuel and the cladding types, into their reactors as LTA programs, lead test assembly programs. This is in addition to the substantial amount of research that is going on at the national labs and other facilities looking into the post-irradiation examination of these LTAs and also the non-destructive evaluation post-irradiation in these facilities. So now I'm going to talk about the back end briefly, and specifically to our ESCAPE collaboration meeting, where we had a workshop on the impact of advanced fuels for the back end. So this is a high-level summary of the ESCAPE program, Extended Storage and Collaboration Program. It's about 11 years old now, and we now have 675 members from 22 countries. In the meeting, we had over 185 participants representing 10 countries, and we have 4 subcommittees. I'm the lead for the thermal subcommittee for the ESCAPE program. And what we did there is we wanted to have this workshop on advanced fuels impacts on the back end back last year. So it's about a year old. And it was broken down into 4 different sections, which was the description of the ATF concepts, kind of like what David was presenting today. The used fuel program updates so that the fuel vendors could then understand what the used fuel perspectives are, because of, as David was showing, you know, in the United States, we've been focusing not just on operations, but on both the front end and the back end. And so in this case, we were presenting the fuel vendors a perspective of the used fuel programs in the United States. And then we had the fuel vendors present their advanced fuel program, their advanced fuel development programs. And then we had a panel discussion on the impact for the dry storage that included NRC, the 3 fuel vendors, and myself. Sorry, not the 3 fuel vendors, the 3 dry storage vendors. So when we looked into the potential impact for the back end, we looked into both the spent fuel pool, dry storage, centralized storage, transportation, disposal. And in this case, what we had here, the consensus was that coated claddings by themselves have very limited impact on the back end operations. There may be some small changes here or there, but for the most part, it's not a very big impact. Higher burnup and enrichment have a potentially greater impact depending on the level of enrichment and for the level of burnup extensions. And so that is a dependency clause, if we want to call it that, for this particular impact for the higher burnup and enrichment. Primarily for these concepts, coated claddings with a higher enrichment and higher burnups, the issues are across the board criticality. Okay, and so having to get more benchmarking and more data to support the criticality analysis is going to be important. Thermal management is a secondary issue as well, meaning that if you have higher burnup, you may be having higher temperatures. So getting more understanding of the thermal impacts and then also the accident analysis thereof. Another area that for dry storage that NRC has identified is the need for the cladding properties, the mechanical properties, so that they can do an analysis to show during accidents and such that, and transportation, that there can be a safety finding made. So a high-level summary of the research that's underway now. We're working with OECD NEA on the KIT quench testing program for high temperature oxidation and coating stability. Also, as Mikhail mentioned, the IAEA coordinated research projects that he identified earlier. We're doing some work on hydrogen pickup and permeability modeling. Also, the coated cladding performance, balloon and burst, and fuel relocation. This is an area where DOE, as part of the workshop from last year, the Department of Energy in the United States is looking into developing a report that's expected in 2021, looking at the data needs for ATF and higher enrichment, higher burnups for the back end. So what are the data needs and how are we going to get them? And that's going to be a report that is expected next year. We are just underway starting these 2 efforts, looking into decay heat testing and modeling, and then spent fuel criticality modeling as a result for these new ATF concepts with higher enrichment. This workshop I've highlighted here is in 2 weeks, and it's on sensors, and that goes to addressing one of the thermal area and other areas of looking into. One of the areas that we're thinking about is when you have new fuel concepts, how are we going to be able to maybe change the approaches by collecting data, as opposed to we had to spend a lot of money in the United States looking at high burnup fuel in a cask and have it stored for many years, and it was very expensive. And we're looking at ways to possibly collect that data for other fuel concepts, such as advanced fuels, so that we can get the understanding of the behavior, long-term behavior, and long-term spent fuel safety issues by using sensors in the long run. So, summary, EPRI is providing independent assessments, and you can download. These are the 3 documents here. You can go to EPRI.com and go into the search feature up on top of the page, put in these report numbers, and you'll be able to download these 3 reports. We have a proprietary report looking at coated claddings with dope pellets, We also have a second update on this document here as well, and so that's also proprietary. And there are several other fuel optimization or fuel utilization reports that are also proprietary. We are looking at these are the three areas that we looked at, looking into the impacts of ATF and higher enrichment, higher burnup. We had last year's workshop, this year's winter program, and then the sensor workshop coming up in 2 weeks. And with that, I will end and take questions.
Thank you very much, Al, for providing this very comprehensive overview of the excellent example of the American nuclear industry, anticipating the challenges of the deployment of accident-tolerant fuel in this integrated manner, gathering all potential actors in the work. So now we have 24 minutes for discussions, for Q&A. So please type your questions in the chat. And so we have a question for David. Can you please elaborate on how the assessments you have described for ATF may apply to other innovations currently under consideration, as, for example, the small modular reactors?
Sorry. From my perspective, I think the thinking is largely the same. Learning from the experiences of previous decades, I think it's important that where we have new fuel types or significant variations on fuel types, that as those things come towards the point at which people think they're viable and want to put them in reactors, it really behoves on us as an industry to look at how we will manage the back end, whether it's going to have a significant impact or not. And if it does, make sure that we are ready for it when it comes out of the reactors. It remains unlikely that the back end will ever drive what goes into reactors if that looks like a viable technology, but it's about giving us the best chance to manage it cost effectively thereafter.
So other question that that I will address to Mikhail, I think it's for you. There is a question on why does the chromium-coated fuel reduce hydrogen production so much better than the other ATF designs?
Yeah, I have already written my response. Yeah, briefly talking, because of increased corrosion resistance of chromium, which can be explained more microscopically, which is related to low oxygen diffusivity through the oxide scale. Related.
Okay, thank you very much. We have a question for Al. So, Al, has the U.S. regulator been engaged by the American industry on the spent fuel management aspects of these new advanced fuel concepts? And if so, if it's a holistic consideration of these advanced fuels are considered for the entire fuel cycle?
Yes, I think Ricardo also identified in the chat or the Q&A that the NRC's issued a report on the data needs for the back end. That's NRC's been completely engaged. It's been a real good dialogue between the industry and NRC. NRC has developed an intra-agency task force, basically looking into a lot of these holistic issues from the front end all the way to the back end, from fuel cycle facilities to transportation of fresh fuel, all the way to in-core operations, to then spent fuel pools, to then the back end. And so it has been a very good dialogue, and I think that we're getting to a lot of understanding between the two sides into how we're going to progress with licensing and identify the data needs and then going after and trying to do this in a more streamlined way and a more targeted way to collect data that is needed for the safety cases. So yes, the engagement with the U.S. regulator has been numerous and has been very helpful to focusing the R&D programs going forward. And I think that in the coming years, we're going to be spending much more time on the back end, looking into the how we can streamline that side for these new advanced fuel concepts. And it's not just these concepts; it's also going to be, SMR fuel and all these other possible concepts down the road. So there's got to be a way, because if we have the luxury right now of just having UO2 fuel with up to 5% enrichment. In the future, it's not going to be as simple, and as a result, we're going to have to figure out ways to either simplify it or get a lot more data.
Thank you very much. So we have a question. Okay. So there is a question that I think maybe is for David. It's for higher enrichment fuels. Will this affect the spent fuel management, particularly decay, heat, and criticality effects? For example, with the number of assemblies per transportation and disposal, can there be affected? Can you explain?
So yes, if you go to higher enrichments in order to get higher burn up, the post-irradiation fuel inventory will be higher and the heat load will be higher. So that might mean that the number of fuel assemblies you can put in one canister might have to change, or the design might have to change to improve the heat transfer. Although a lot of work on improving heat transfer out of storage casks in particular has been done over recent years. And certainly, I think for high burn-up fuel, high enrichment fuel, high burn-up credit is going to be more important in order to prevent us having to fall back on unirradiated criticality assessments. But there still is a challenge on that we need to work out to make the safety cases for very high burnup or high enrichment fuels, to actually work out how do we make the cases that allow a cost-effective deployment and management in the back end.
So can I add a few things, David, to that? So we talked about this significantly during the 2019 workshop, and what we found there was that the flux traps, additions of flux traps within the canisters, if the enrichments and the criticality analysis were substantially different, and that would create a design change, and also, as you mentioned, David, a reduction in possibly the number of assemblies per canister to load. That was found to be very problematic by a lot of folks in the meeting. And so that was one where the vendors said that there may be ways around that, but of course it might be dependent upon a lot of information and data that would need to be provided in terms of what the expected end of life of the spent fuel characteristics would be. So that was an area of importance. The other area was also not just the thermal aspects, but also the dose aspects, and in particular the steels. There are operational examples out there of facilities that used stainless steel. We used stainless steel prior to going to zirconium alloys, and in particular, in one case in the United States, one set of transportation has to be delayed by almost a decade compared to the Zirc fuel that came out much sooner because of the activation of the stainless steel. And so you have a higher dose in that you can't transport those because you'd be above the dose limits. So So your time to when you can also take the fuel out and transport to a centralized facility or an interim facility could also be delayed by going to some of these concepts.
Thank you, Al. So let's move now to front end. Again, so Mikhail, this question is for you. It's so far potential safety enhancement achieved by ATF have been mostly focused on reducing clad oxidation and consequently hydrogen production. But what if temperatures reach to a level where the new cladding materials and coatings start forming eutectics? Has this aspect been given enough attention so far?
Yeah, good question. Yeah, this is one of the, because you see, research is going step by step. Up to now, it was more focused on normal operation condition and local conditions, where these effects are not so important. But going above 1200, somewhere at 1350 centigrades, eutectic for chromium with zirconium is observed, and this is currently under investigation in many research centers, in Karlsruhe, in France. Not only. And also, of course, if we go further to higher severe accident conditions, then you can read it in KIT, for instance, presentations, recent presentation at different meetings, when they observed very strong oxidation of silicon carbide at 1800 centigrades. Okay, so all these new materials more or less are maybe better than zirconium under normal operation conditions, not bad for local, but they are still under research for severe accident conditions. And of course, eutectic formation, one of important topics.
Thank you, Mikhail. There is a question maybe for David. So do you think that overcoming ATF operational challenges may also solve most of STEM ATF management challenges as a result? So can we conclude that finding a correct fuel plus cladding formula for safe operation would also mean save the backend investment?
It would certainly help. I think it takes us a long way down the road of having a material that performs well and therefore performs at least as well as UO2. However, chemistry is not that simple, and the time scales over which we're interested in terms of the back end sometimes generate different phenomena that become the limiting factors in assessing whether, for instance, cladding integrity is maintained under accident abnormal conditions, or even simple things like the matrix dissolution rates within a repository. So I think we can't assume that anything that will survive a reactor will be compatible with the current way of managing fuel in the back end. Having said that, I think it's quite likely that we will be able to devise an adequate method of managing that fuel, but we need the time and the data to do it. And that's one of the purposes of making sure that we do these assessments in good time.
Thank you. So we have 10 minutes ahead. I think we can have another round of questions. So there is a question for Al, and it said that was the reduction of number of assemblies per canister factored into the EPRI cost analysis?
So I responded in the chat, and
okay.
not at this time. because of the uncertainty with the enrichment and burnup levels. What the panelists discussed was that for small increases, there probably wasn't that big of an impact, but at some point, you know, we're going to have to look at this as a function of enrichment and discharge burnup levels, and so it's just too uncertain at this point. But we will be looking into it in the future.
Okay, thank you. There is a question for Mikhail. So, Mikhail, is there a study on the ATF behavior once an accident-tolerant fuel becomes corium in terms of reaction to reactor internal pressure vessels and its heat capacity and flow behavior?
You mean under severe accident conditions, yeah? Where?
Yeah, I think so, yeah.
Yeah, I think it, as I already mentioned, there are very few experimental data under severe accident conditions. What I know mainly in KIT, when they performed separate effect test with very high, with one single rod of different candidates at very high temperatures, and where behavior was not really good. And for this reason, there are no enough data, even with hydrogen. You remember prediction for Thickrell in the Quench 19 test, prediction of hydrogen were strongly underestimated because available correlations for this material were measured at lower temperatures. So when participants automatically applied, extended these correlations to high temperature regime, they obtained a strong disagreement. So for this reason, currently there is a strong lack of severe accident data. This is one of the reasons why we are planning to have new tests under severe accident conditions at the Japanese facility. And also probably you know NAA, OECD NAA, new research project, which will be a new test will be performed at the KIT Quench facility. So for this reason, as I already told you, experimental data is the key point now, but nevertheless, severe accident codes are trying to model this. For instance, it was mentioned by Al in his presentation. He showed some examples of calculations by Melkor, if I'm correct. Yeah, but this, to my mind, is very preliminary results demonstrating that owing to higher oxidation resistance at low temperatures, we can, which is better understood now, we can expect extension of so-called coping time. So the time where the fuel rods are at relatively low temperatures. Okay, thank you.
Thank you very much, Mikhail. There is a question, there are two questions on disposal. So maybe, David, you can address them. So one is, does the fact that 50 years ago, deep geological disposal was not so much considered at the fuel design phase impact the ATF development comparing to the standard UOX fuel?
I don't think so. The research and the development work that's gone on has established a way of dealing with UOX fuel, and that becomes the reference case. So the comparisons we do then is to look for are there any aspects of advanced or different fuels that would make it worse than the current reference. So I think actually for ATF, the case in some respects is easier because we have a reference case that we believe we can manage and dispose of safely. So we have something to compare it against, and therefore it helps us to focus our attention on the aspects or the characteristics of ATS that may be different in a way that we might challenge any of the assumptions or the modeling or the chemistry that we assume for repositories. I think the only other aspect is, in addition to thinking about what might be different, I think there's also an element of when we have those materials confirming that behavior is as we would expect it.
We have a question from Por Al, and I think it applies more to US examples. So there is a question on what are the main challenges for higher enrichment fuel, more than 5% of enrichment for the industrial deployment?
There are a few. The number one issue is regulatory, which is that, well, I shouldn't say number one. The number one is that we can get through with exemptions and then rule changes, that there is a rule that says that we can't store greater than 5% in spent fuel pools, but that can be overcome through exemptions and such. But the most, I think, from this is a technical question. Then the technical question would be that there is the higher enrichment. You can get to higher burnups, and the burnup is really where the issues that NRC and others have identified through research and testing. And so with that, it's really tied to the higher burnup, what happens to the fuel, what happens to the cladding, with the coatings on top of it, that maybe you can get to higher burnups, which then enables the enrichment. Because you don't want to have a higher enrichment if you can't get to longer, more efficient use of the fuel, meaning that you can use the fuel, because enrichment, U-235 equals dollars. More U-235 equals more. It's more expensive, and so therefore, you need to really think about the burn-up aspect, which is what's going on right now. There's a lot of activities looking into burn-up, and also in what we're looking at here. If you look at one of my latter slides, I talked about spent fuel pool criticality as another area that we need to get working on. So I would say, from a technical point of view, higher burn-up that allows the higher enrichments, and then the criticality associated with spent fuel pools, and also all the analysis that you have to do for in-core operations. But for the back end, it will also, like I showed on that one graphic, criticality, temperatures are, I think, the two biggest areas impacted.
Okay, thank you. So we are ending the webinar. So there are few questions in the Q&A chat, and I'm going to propose that we are going to copy them, and then they will be answered by the panelists. So the webinar will be available, the presentations and the webinar will be available in the SFM network that most of you are members, because we have the list of participants. There is a banner dedicated to webinars. So there you will find the record of the webinar, the presentations, and we will put a PDF with the questions that are not answered because we don't have time by the panelists. So I would like to thank you very much, the panelists, for their efforts and the very, very interesting talks, all the attendees to be there, and also for all the questions. It was a very lively webinar with a lot of interaction. And thank you very much, everybody, and please stay safe and healthy. Thank you. Bye.
Thank you.
Thank you very much.
Thank you.